Okay, let's start. Any questions from the last lesson? Everything good? Everyone knows what the vector space of linear operators is, how to take inner products of them, how to find decompositions of them. Yes? Okay, I presume all of you are experts right now. Okay, very good. Alright, so hopefully today maybe it will spill over to the next lesson, but hopefully not. We will finish the mathematical preliminaries. I stress again that I hope everything I've said is nothing more than just a recap of what you've learned in linear algebra before. Because, okay, so question. Is it a recap for most of you, or is it something new? Is it really new? Not new.
It is new.
Huh, sorry?
It is new, yeah.
It is new. Oh, that's bad. I mean, that's good that I'm going through this, but it's also bad because I hope that it would have been. But like which parts are new actually?
Most of it.
Most of it, really. But the concept of like linear independent spaces, vector spaces.
It's intuitive, it makes sense, but the concept of it is new.
Oh, but was it not covered in your previous like linear algebra class?
I think most of us, if we just follow the physics syllabus, we don't take linear algebra specifically.
But to take quantum mechanics, you have to take linear algebra. You have to take it. No?
No, it's just mathematical methods one.
Oh, that's true, but
Yeah.
don't they cover linear algebra there as well?
They just cover like finding eigenvector, eigenvalue, and
Without covering what the vector space is?
yeah, they don't really go to the abstract part. They just focus on the computational aspect. So
I
like
believe
matrices and stuff.
Most of what you're going through now is in the first portion of Mathematics 2.
Okay, then they should stop. Okay. Alright. Okay, so I am gratified that we are going through this and you're learning something new. At the same time, that's not great because that means that we spend 50% of our time learning math, and then only the second half of the semester we begin talking about physics. But I can't do it the other way around, because if I talk physics without the math, then you will not learn anything. Or at the most, you'll just learn how to wave your hands and say that this should be that, but that's not quantitative. Okay, so never mind. Let's continue. We will hopefully finish up with eigenvectors and eigenvalues. Hopefully, this is stuff that you have encountered as a computation at least. But again, as a recap, so states. This is a vector, the quantum state, and encompasses physical reality. It has all the concepts of, it lives in a vector space, there's all the concepts of basis, superposition, different realities can be added to each other. Then we identified a few classes of linear operators which are very important. H, Hermitian operators, which happen to be in one-to-one correspondence with physical properties. So again, what you're doing, hopefully you see that is that you're learning math at the same time as you're learning physics. We have mathematical formalism, but also physical interpretation. Okay, unitaries are the ones that rotate you, so they generate evolution. Because we saw from last lesson that the unitaries are the ones that preserve the norm or the inner product between vectors, and in particular they preserve the norm of a state, which means that if you have a state which is initially normalized, and you apply any unitary, it's going to remain normalized, and so we can retain the meaning of probabilities, and that allows us to get meaningful predictions in physical realities. Okay, good. And then we saw that the relationship between the two of them is that unitary is the exponential of some Hermitian operator, e to the power of I h. Some of you ask, do I write a plus or minus there? Who cares? Doesn't matter. If h is a Hermitian operator, minus h is also a Hermitian operator. So the point is that you raise it to some, you exponentiate it, and you multiply it by the imaginary number, that gives you unitary. So either way works, okay? There will be some permission operator there. And vice versa. Take the matrix logarithm and you get this. Okay, so let's now talk about the properties of the operators themselves. So remember that a linear operator is one which maps, so suppose I have a linear operator T, it maps some vector alpha, some vector beta. So in general, it's going to map me from one point to another point, alpha and beta, where this is V, vector space, under T. But suppose I could find a particular vector where under the action of this operator, it simply maps vector itself, maybe this gamma here, maps vector itself under T up to possible rescaling. So that means that we're trying to find a special vector where, let me denote that by big lambda. Okay, so maybe I should call this big lambda. Where I apply the operator onto it, I get vector itself up to a possible rescaling of lambda. Where this could be any value. It could be 0, could be 1, could be I, could be 2 plus I, whatever it is. Well, suppose I could find that. Then what this is, this pair is an eigenvector pair for T. Of course, maybe you can find more. You can find a different lambda, then you can find a different small lambda as well, and that will be a different eigenvalue pair, eigenvalue, eigenvector pair. Okay, how do we find this? Okay, so here I'm going to be a bit procedural, computational. I won't go through the abstract math, but essentially, if you have a linear operator here, then what you do is that you write it in terms of its matrix representation in some basis. So this would be some matrix T00, T01, T11, T10, blah, blah, and so on and so forth. Then if you construct this, if you take the matrix and you take away lambda multiplied by the identity. So you see that I want to make things consistent, right? So I can only subtract a matrix from a matrix. Lambda is a constant, so what I really mean is that I'm subtracting off constant times the identity. This is a new matrix, that's fine. And then if I find the determinant of this guy, which I presume all of you know, I will not go through this. Then, solving this, you set this to be equal to 0. On the left hand side, for any finite dimensional matrix, if you expand this, you'll get some polynomial in lambda, which is called the characteristic polynomial. So let's call this P of lambda. And so if you solve for the roots of this guy, you set this to be 0. Solving for such P for the roots, such lambda, sorry, yields the eigenvalues. So this is a procedural way of finding the eigenvalues of an operator. So you express the operator first in terms of some matrix, then you find this, you subtract off some lambda from the diagonals, find the determinant, and solve for when the lambdas is, when this polynomial is 0. And then the solution is going to be the set of eigenvalues, also called the spectrum. And the reason for the word spectrum is because it has a lot of connections to the theory of light. So it tells you the colors of the matrix, for example. What is it decomposed in? Red, blue, green, whatever it is. But it's not a strict analogy, but I'm just saying that there is a interpretation of the numbers lambda as being the colors of the matrix, different colors. And then to find the eigenvectors, okay, so that's the first step, right? That's how you find the eigenvalues. One. The second step, to find the eigenvectors, you take one, okay, so if you solve for such lambda and you get, say, lambda 1, lambda 2, lambda 3, whatever it is. To find the eigenvectors, you take an arbitrary column vector, A, in this same basis, and then you solve for when, for a given eigenvalue. And then this solving for A gives the eigenvector associated with lambda 1, lambda I. Okay, so let's call it AI. Because for each lambda I, you get a different eigenvector. And, okay, one thing you should note is that eigenvector is not unique, right? Because you see that I can arbitrarily scale this eigenvector by any scalar, then both sides will still be satisfied. So once I've found one eigenvector, then I have infinitely many same eigenvectors, but they're all basically just scaling of the first one, or one of them. So you can always choose a convention where you set them, you can always normalize the eigenvectors. Okay, we'll see a specific example. Okay, but here I want to give you the, hopefully, procedural math methods 1 has covered this, so you know this. Good. And then, how do I go back to the dyadic representation? Remember that I went from the dyadic representation here, I went to the matrix representation here, I'm looking at matrix representation. So the eigenvector associated with this eigenvalue lambda I will be given by all the coefficients AI and then over the basis I, where AI is the components. Oh, sorry, this is a bad notation. Okay, let's call this A N N. Okay, so this is a bit bad notation, but what I'm trying to say is that for the eigenvalue and eigenvector, we get some column matrix. We get a column matrix of AI1, 0, AI1, and so on, and AI, E minus 1. And so this encodes the coefficients over which we should expand in the basis. And then that gives me the eigenvectors. Okay? Let's have an example. Let me leave the instructions on the board so that you can always refer to it. Let's go back to our favorite example. Let's take two-dimensional vector space and the operator sigma x be 0, 1, plus 1, 0. Okay. So if I give you this operator, I ask you, find its eigenvalues and eigenvectors. Okay, so let's proceed. First, let's express it in terms of a matrix, and the one choice could be expressing in the basis of 0 and 1, as it's written here. We don't have to, but let's just do it. Okay? So the matrix sigma x in, so the matrix rep of sigma x is 0, 1, 1, 0. Everyone clear, right? We just quickly did this. Okay, then next step, we find this polynomial. We construct this matrix, which is the matrix 0, 1, 1, 0 minus diagonal lambda, and then we find its determinant, which is equal to the determinant of minus lambda 1, 1 minus lambda, and I trust everyone knows determinants, so that's equals to lambda squared minus 1, and you see that this is a quadratic polynomial, and so let's solve for it. Solving for roots of lambda squared minus 1, we get lambda equals plus minus 1. Okay, so if I use that convention, I should say the first eigenvalue should be 1, second eigenvalue should be minus 1. Right? Both of them are roots of this polynomial. Okay? Then next, let's find the eigenvectors. So we take the matrix 0, 1, 1, 0, and then we input in an arbitrary vector, A1, A2. Remember that this is the basis of the 0, 1 vectors. And let's suppose that we want to find the first eigenvector. So then we say, I want this to be equals to lambda 1, which is 1, times of A1, A2. Okay, so that's the first eigenvector. First eigenvector is basically this one here. Okay, so what we get two equations. If we expand the left hand side, this is equals to A2, A1. So what we see is that we're trying to solve an equation, and we know that we should set A2 to be equals to A1. And we also see that the second equation is the same as the first equation. So that's the degree of freedom I'm talking about, that we can scale this vectors arbitrarily. Right? So we get, so let me erase it there and continue here. So we get that A1 equals to A2. So the conclusion is that eigenvector is of the form A1, A1. Or you can always write it as A1, 1, 1. So again, I stress that the eigenvectors are not unique because we can scale them, but we can choose convention. So here's more for convenience than anything else. It's important, but it's more for convenience at this stage. We can choose to normalize out of convenience. So if I normalize this vector, what should A1 be?
1 over root 2.
Yeah, great, thank you. Yeah, 1 over root 2. Everyone got that, right? Because we want to just multiply by a number such that this guy has norm 1, and we work it out as 1 over root 2. So that would be 1 over root 2. Then, that's eigenvector. But then to convert it back to the dyadic form, we just read off. So my eigenvector lambda 1 is equal to 1 over root 2, 0, plus 1 over root 2, 1. How do I get this? Well, this is the first coefficient, that's the second coefficient, and that's it. And then we can do a check. If I apply sigma x onto this lambda 1, I will get 0, 1, plus 1, 0. Okay, so that's the operator, multiplied by the state. And then if I work it up, equals to 1 over square root 2, 0 plus 1. You can see that, right? The 1 only affects this guy, that becomes 0. The 0 only affects this guy, that becomes 1. So 1 over square root 2. So that's equals to lambda 1 itself. And so the eigenvalue here is real. So don't forget, there's a number in front here. The number in front here is plus 1. Okay? So the eigenvalue is plus 1. So very good. We have verified that what we found is an eigenvector pair. Now for the other one, let's repeat the same analysis, and I'll just write over what I have using the different color. So now to find the second eigenvector, oh, this is not blue. It's a blue one. Can't see anything. So I'll use red, hopefully you can see it. You want to find the second one. Second one, you put a minus here. And the left hand side is still the same. But then once you try to solve it, you find that the second eigenvalue requires A1 equals to minus A2. And therefore the second eigenvector is of the form minus, minus. And again, we can choose to normalize our convenience, so we get this. So the second eigenvector, slash 2, I'm just making this notation of like 1 or 2, is plus or minus. And if you do the check, if you apply sigma x onto 1 or 2, first you apply on 1, you get that. If you apply on 2, this will be a minus. But then you will get a minus here. And that's equal to plus minus. Okay? Great. Awesome. Okay, very good. So we have diagonalized our first matrix. And we see that there's two eigenvalues, plus 1, minus 1. And there's eigenvectors there. Okay, now I'm going to erase the procedural way and teach you a few more tricks on how you can analyze this without going through this procedural method. So I also want to stress upon you that there are infinitely many ways of solving a problem. And the way that's been taught to you is a recipe, but you are, of course, welcome to invent your own recipe. And you just have to show that it's right. Okay? There's not one way of doing things that must be adhered to. In fact, that's how new science and new math gets done. You invent new methods. So in this particular case, let me present a couple of new ways of doing it. Interestingly. Let's compute sigma x squared. But we did this already in class. So if you expand it up, you get 0, 1 plus 1, 0, 0, 1 plus 1, 0. And therefore we get, this is equal to 0, 0 plus 1, 1. And that's equals to identity. Okay. So let's suppose that I have an eigenvector. I'll drop mouse to figure out what it is and what eigenvalue can be associated to. So by definition, it's saying this. I should be able to find a lambda that gives me back, a small lambda that gives me back a big lambda. But now let's apply sigma x twice. Let's apply sigma x again here. On both sides. On the left hand side, I just calculated that sigma x squared is identity. So I should get identity times lambda. On the right hand side, I'm applying sigma x onto the vector big lambda. The reason is because this is just a complex scalar, so it just comes out. But then sigma x times lambda it satisfies again the eigenvector equation. Right here, this one. So that's equal to lambda squared. So what do we conclude? We conclude that lambda equals to lambda squared, lambda, if it's an eigenvector. And since we're assuming that the eigenvector is not vanishing, which means that it's not a null vector, then we are allowed to cancel both sides. Okay, for those of you who think that that's how can I cancel a vector from both sides? You can take the inner product of the vector with itself on both sides, and then that becomes a non-zero number, and then you can cancel the number. So we get 1 equals to lambda squared, and therefore you get that lambda should be equals to plus minus 1, just like before. And then you can solve the eigenvectors after that. Okay? So here's a nice way of, at least for this particular problem, you can stare at it and say that, I see the observation that lambda sigma x squared is to 1. Clearly it means that eigenvalues plus minus 1. And if you can convince yourself that if you have a matrix that cubes to 1, let's say, then the eigenvalues are going to be the cube roots of 1. If it raises the 5th power to 1, then the eigenvalue is the 5th power of 1, and so on and so forth. Again, for this particular exercise, or this example, there are more ways to solve it by inspection. So again, let's consider sigma x acting on 0. If I act it on 0, then you see that it's going to send it to a new vector, but the only vector it sends it to is 1 vector. So it's equals to 1. Right? Like that's the action of the operator. Everyone forward? Same thing, if I apply it to 1, you get 0. So that's what it means. The operator acts on the basis vector, it sends me to some other vector. In this case, it happens to be 1. The second line happens to be 0. And here's the trick. Why not just add the 2 of them up? Now if I add the 2 of them up, then the left hand side, by linearity, becomes 0 plus 1. And the right hand side becomes 0 plus 1. And you're like, wow, I found it. I found an eigenvector, right? I found something that when I act the matrix on, or operator on, it returns itself. And so we see that the eigenvalue is plus 1. You can repeat the same analysis by observation. Why don't I just subtract them? And then I will get minus 1, minus 0 plus 1, which is equals to minus 0 plus minus 1. And so I found the other eigenvector. There, okay? Many ways of solving it. Good. Now let's move on to a bit more theory. We don't really have much time. Okay. Now let's look at the second example. Let's look at this example of, say, I'm going to call this operator sigma plus for historical reasons, and this is just going to be 0, 1. And I could ask, what is the eigenvectors and eigenvalues? Again, let's write it in matrix form. So the matrix form of sigma plus is equals to 0, 1, 0, 0. Now if I subtract off the multiple of the identity, I will get minus lambda 1, 0, minus lambda. And then if I find the determinant of this guy, I will get lambda squared minus 1, no, minus 0, sorry. Equals to 0. I'll get lambda squared minus 0 equals lambda squared. And then I want to solve it, I get 0. So this means that lambda equals to 0. So if it has an eigenvector, it should be equal to 0. I mean, it should have an eigenvalue of 0. So now let's solve for the eigenvectors. So let's do 0, 1, 0, 0, multiplied by a1, a2. And then I want this to be equal to 0 times of a1, a2. If I expand it, I will get a2, then this is 0. Right? And then I want this to be equal to 0, 0. So the conclusion is that a2 should be 0, and a1 is free. So the answer is that the eigenvector looks like this: a1, 0, or there's a1, 1, 0. And if I write it in the cat form, that's equals to, and then if I normalize it, so if I normalize it, out of convenience again, there's just 1, 0. So the only eigenvector I have is just the same 0. And you can see this from inspection, right? If I add sigma plus onto 0, it kills it, makes it vanish. And that's a perfectly good eigenvector, eigenvalue pair. It's just an eigenvalue of 0. Okay, so just because it vanishes doesn't mean that it's not there. We'll make this mistake. Okay, people make this mistake all the time. Okay, 0 is a perfectly good eigenvalue. Okay, so again, consistency check. Sigma plus acting on this equals to 0. And by 0, I mean the noun vector, more precisely. Okay, so eigenvalue is 0. But we see something a bit troubling happening here. We see that even though this was a 2 by 2 matrix, and we went through this procedure, we only found one eigenvalue and one eigenvector. Whereas in the first case, it's again a 2 by 2 matrix, and we found 2 eigenvalues and 2 eigenvectors. Now let me ask you this question. If I have a 2 by 2 matrix, could I find 3 eigenvalues and 3 eigenvectors? Could I find 4? So what sets how many I should find? Like you see 2 very drastic examples. Even though the same size matrix, obviously not the same matrix, but 2 by 2 matrix. In one case, it yielded 1 pair. In the second case, it yielded 2 pairs. So how do we tell? Okay, so that leads us to a very important theorem in linear algebra. So this is called the spectral theorem. For Hermitian operators. So what is it saying? It's saying that if H is Hermitian on a d-dimensional vector space, to be precise, complex, then it has the real eigenvalues and the orthonormal eigenvectors. So let's call the eigenvalues lambda I, and let's call the eigenvectors big lambda I. So there are two characteristics of it. One is that lambda I is real. And two is that these eigenvectors can be chosen to be orthogonal. In fact, orthonormal. This is a very powerful fact because it guarantees you a condition. Like it allows you to determine when a matrix is fully diagonalizable by only checking whether it's Hermitian or not. Okay, so as long as you can see it's Hermitian, then it has this. In fact, the first matrix that we did over here, we found that it was Hermitian, right? A few lessons ago. So it satisfies that. It's a 2 by 2 matrix. It has two real eigenvalues, we saw that, +1, -1. And it has two eigenvectors, which I remind you, so the eigenvalues were +1, -1, and the eigenvectors were 1 over square root 2, 0, +1, and 1 over square root 2, 0, -1. And we can check that these two are normalized and orthogonal in accordance with the theorem. So the theorem works, right? And one more remarkable fact is that we also learned that the identity operator can be expressed in any orthonormal basis as an outer product. We learned this, right? We learned that identity can always be written as some outer product in some basis. But then, because we have the orthonormal eigenvectors, this necessarily form a basis. So the spectral theory guarantees, as a consequence, okay, it's not part of the theory, but it's a consequence of the theory. This implies that the eigenvectors of any Hermitian operator satisfy identity equals to lambda I, lambda I. So we can use it to deconstruct the space, the entire vector space. Essentially, the eigenvectors of the Hermitian operator they form an orthonormal basis. So we can always decompose the vector space into its subspaces. Okay. The full proof of this, okay, how many of you have not seen this? Everyone has seen this, right? Good. So it's either yes or no. Who has not seen this? You all took the name of it. At least it's stated. I'm not saying even proving it, but just like stated. No one has taught you this? Holy shit. Okay. Who has seen this? Okay. Well, I guess first time. Alright, so let me say a few things. First of all, let's prove one or two facts. Okay, I'm not going to have a full-blown proof of this. That's too much for this class. Let's at least see how this happens. Why real? How come? Okay, so we can do this. Suppose that we have an eigenvalue of this Hermitian operator. Let's call it lambda n. Sorry, small lambda n, and the eigenvectors is big lambda n. Then let's sandwich it on both sides by big lambda n itself. Okay? And let's assume that it's normalized, because we can always normalize that vector. So the right hand side just becomes small lambda n. The left hand side is this. Big lambda n, h big lambda n. But then, because this matrix is Hermitian, I can write it as H dagger. Sorry, I can use it adjoint and write it this way. So by definition, that's the adjoint of the operator. And then I can also swap the ordering up to a complex conjugate. This is by the property of the inner product. And now I use the property of being condition to get rid of this dagger. Don't forget the stuff. But H acting on big lambda gives me small lambda times big lambda. And don't forget to start everything. So that ends up being small lambda and stuff. So the conclusion, if we follow that logic, is that lambda n equals to lambda n stuff. That means that it's real. Eigenvalue is real. And that follows from the property of being conditioned. Okay? Some derivation here and there. Okay. Now, let's quickly show the second property, that we can choose it to be orthonormal. I will not show it in full generality, but we can show it for a restricted class. So suppose that lambda n and lambda n are different eigenvalues. So lambda n not equal to lambda n. Then I can say that if I apply H acting on big lambda n, which is an eigenvector associated with the first guy, and then I apply big lambda m here. So on one hand, if I do the evaluation this way first, this will give me lambda n, lambda m, lambda n. But then if I decide to do the evaluation this guy, like this way first, so that is equals to, and I can now swap the ordering. Okay, so I can write it as H dagger lambda m, lambda n, but that's equals to lambda n lambda n, lambda m, sorry, that's equals to H dagger lambda m star. So again, I use a trick that I can swap the ordering by the complex conjugate. And now I use a property of being conditioned. And then I realize that I can treat this as an eigenvector equation. And then I pull out the eigenvalue lambda m here, which is a different eigenvector here, eigenvalue there. And then I make use of the fact that the eigenvalue is real. So this is equals to lambda m, and this is lambda m star. And then one last trick, I can convert that back to lambda m, lambda n. So if you follow that line of logic, if you only look at the first term and the last term, what we are seeing is that we are concluding that lambda m times the overlap is equals to lambda n times the overlap. But we also just assumed that the two eigenvalues are different. So the only way that this equation can be satisfied is if the overlap itself is 0. Then 0 equals to 0, and that's satisfied. If it's not 0, then it's clearly not satisfied. So that's conjugation. So So we see that we have at least shown in a case when eigenvalues are different that they are orthogonal, and I guess you can always declare that they can be normalized. Good. All right. And I guess maybe I shouldn't rush this. We'll continue next lesson about more properties, but let me try to finish up in the next 10 minutes what I want to say for this guy here. Okay. So if I have a Hermitian operator H, now we know that it has real eigenvalues and orthogonal eigenvectors according to the spectrum theorem. Let's believe that. So by definition, H acting on big lambda n on this eigenvectors gives me small lambda n, big lambda n. But why don't I just simply take the outer product of big lambda n here? I can do that. And then let me sum over all n's here. But then I just said that the sum over all the n's, right? I guess I'm changing from I to n, is the identity. So that's equals to just h times the identity, which is h. So the conclusion is that we have the spectral decomposition of the Hermitian operator as h, any h can be written as the sum over all its eigenvalues times the outer product of all its eigenvalues. And we already saw one specific example of that. If we took lambda n, small lambda n's to be 1, error could be 1. Then what do we get? We get the identity operator. And the identity operator is indeed Hermitian. So it obeys the spectral theory, and we can decompose it into its eigenvectors. So in fact, this decomposition that I wrote down here, this like resolution of the identity, can be thought of as a specific case of the spectral decomposition of a Hermitian operator. Right? Let's see in action. I left this up here. So sigma x was this operator. We found this decomposition. Let's reconstruct it. It's claiming that sigma x should be recreated in this guy. Recreatable in this guy. So let's do lambda 1 times big lambda 1 outer product. So we get plus 1 times 1 over square root 2 times the outer product times 1 over square root 2. Oh, wrong way around, sorry. So that's small lambda 1, big lambda 1, big lambda 1. And if I add this to minus 1, this is lambda 2, times 1 over square root 2, 0 minus 1, 1 over square root 2, 0 minus 1, the other way wrong. This is big lambda 2, big lambda 2. Okay. So if I follow the recipe on the right hand side, now if I expand it, I'll get 1 half 0, 0 plus 1 half 0, 1 plus 1 half 1, 0 plus 1 half 1, 1 minus 1 half 0, minus 1, plus 1 half, 0, 1, plus 1 half, 1, 0, minus 1 half, 1, 1. And then we cancel terms. The 1, 1 terms cancel out, 0, 0 terms cancel out. And then we get 0, 1, plus 1, 0. And that's equal to sigma x. So we see that yes, we can decompose that original operator in terms of its eigenvalues and eigenvectors. Okay. We can also check the resolution of the identity. So what it is saying is that if you take the outer product of the eigenvectors of any Hermitian operator, assuming that it's orthogonal and normalized, then that should resolve to the identity. So the only thing that changes if I were to check this relationship or this relation, this one here, is that I don't sum anything here. I just sum a plus 1 here for everything. You see over here I'm summing a small number n, here I'm just summing a plus 1 for everything. So what changes? Now I just make this a plus 1. And then what will change is that this terms become plus, minus, minus, plus. And then terms which are diagonal will not cancel out, but actually these terms will cancel out. And then we end up with 0, 0 plus 1, 1, which is the identity. Okay, so we have checked that. This was example. I want to stress another thing is that when I say that it has d real eigenvalues, I did not say anything about there being distinct eigenvalues. They could be repeated. So for example, the operator could have three instances of one eigenvalue of 1. We already saw that, in fact, for the identity operator. It has eigenvalues 1. And how many times does it occur? It occurs d times. Right? You see that this matrix is really written as a matrix form, looks like this. And then d of them for a d-dimensional space. So each one of them is an eigenvalue. Each one of them is associated with a different eigenvector. And that's called the multiplicity of the eigenvalues. So let me just state it. There could be multiplicity or degeneracies in the eigenvalues. It's just a fancy name to say that they could be repeated. If they're repeated, then just treat them as repeated here. Any questions so far? Good. Good. Now, which other operators can we diagonalize? Turns out that because Hermitian operators are very related to unitary operators, we also have a spectral theorem for unitary operators. So let me just remove it here. And in your notes you can copy, you can write it down as a new paragraph. So now let's change it. Spectral theorem for unitary operators. If U is Hermitian, if U is unitary, then the only thing that changes, really, is the fact that it no longer has d real eigenvalues, but it has d eigenvalues. It will have d eigenvalues again of the form lambda I is equals to e to the power of I theta I, where theta I is in 0 to pi. That means to say that it is just a complex number with unit modulus 1, with modulus 1. So it's just a phase, it's just a phase vector, okay? If in the complex plane, you draw real part of Z, imaginary part of Z, and then this is the unit circle, which is mod Z equals to 1. And the eigenvalues of a unitary operator are such that they always just lie somewhere here. On the unit disk, on the unit circle. Okay? And then what changes? Nothing else changes. It has the eigenvalues of the form, this, phase vectors. Its eigenvectors are also orthonormal, so it satisfies this property. So that means that eigenvectors of any unitary operator also satisfies the resolution of the identity. Again, there could be multiplicity or degeneracies in eigenvalues. And if we decide to repeat the same trick as we did for the Hermitian operator, if you put a U here, now the eigenvalues are of this form, e to the power of I, theta I. Please don't confuse this I for this I. I know it's bad notation, but this I is a complex number. This I is just an index. It's clear for me, at least from context, what is what, but it could be confusing for first timers when you see I and I and say, oh, does it mean I sum over the I here and also the sum over the I? No, this I, the first I is just a complex number I, the imaginary number I, and this I is the index. I should really call it N, but never mind. Okay. So this is so in this formulation is easier because I don't have this ambiguity. So it's e to the power of I theta N. And so the spectral decomposition of a unitary operator is any unitary operator can be written as e to the power of I theta N lambda N, so on and so forth. And what are some examples of unitary operators? In fact, this guy, again, is not only Hermitian, it is unitary. So your favorite example has many properties. It's also a unitary operator. How do I see that? If you take the adjoint, it's itself, and then if you take sigma x adjoint times sigma x, that's equal to the identity, right? We proved or we showed from the whole exercise that sigma x equals identity, so it's unitary. So it's not only Hermitian, it's also unitary. So if it's unitary, it means that spectral theory also applies. And it means that eigenvalues must fall inside the unit, well not inside, but on the unit circle. And we found that this was +1 and -1. And we look at where they are in the unit circle. They are precisely here and here. And so yes, they obey the spectral theory. And they obey clearly the spectral decomposition. And clearly, you can write +1 as e to the power of I0. And clearly, you can write -I as e to the power of I pi. So everything checks out. All right, let's have a tutorial. Let's break for 5 minutes and then TAs will set up the tutorial session. I guess I didn't manage to finish everything I wanted to go to, but we're very nearly there. So we'll finish up on projectors and also like more discussions about eigenvectors and eigenvalues and stuff, probably in the half lesson. All right, Richard, Zeno, do you mind setting up stuff?
It's not sleeping. She's not very cute. Yeah. Really? It's just compute. Remember what you translate?
Okay, that's fine.
Just like how a car mechanic, I just understand how a car works.
Okay, so again, I think it's uploaded on Canvas, so if you can't see it, just look it up on Canvas. Let's give it a try. So solidify your understanding of unitary linear operators. And then we have here to answer your questions. Have to check with us. So exercise 13 on functions of operators. I wanted to go through it today, but no time to. But you can give it a try anyway.
Of course we do. Does it look like this? Pretty much.
The points are the same.
How about the label 0.1 to 1.1? I mean the scale.
Yeah. You know, I can't remember. I mean, there were like 7 graphs there. 1, 2, 3, 4, 5, 6, 7, 8.
Then what's the unit? Let's say I log R. What's the unit for log C?
It's fine, like your gradient wouldn't be affected by your marks.
My gradient wouldn't be affected. No, yeah, but the question is, what do I label my axis? What's the unit start?
Not bracket R/cm.
So my
So I put the units inside the bracket. I feel like I did that for physics practical before. That's
what the hell is log CM?
What?
What is log CM?
I don't know what you did there, but basically that shows the input to the log. Yellow diagonalization again. Or the red
Let's find the eigenvector and then PDP inverse.
Yeah.
No, I think because it's just causing eigenvectors when it's just finding the eigenvectors. I think by finding the eigenvectors and eigenvalues, I should include PDP inverse. Like it's not even from MM1, it's from linear algebra and all I remember, my teacher. Yeah, I just remember my teacher telling me the one thing you need to take away from linear algebra, PDP inverse. D is the diagonal. I think the spectral proposition is basically PDP inverse. Oh yeah. You can write this in matrix form. And then it becomes P is your
No, I say that I wanted to revise this.
D is your diagonal. Don't put the grass and do half.
Oh, you're not gonna calculate the half of it.
I'm not to play for my question.
Yeah, so from the beginning,
For my question.
you get the grading from
You never upload. You never upload the. You want me to fix them? I'm trying to find this thing. Yeah, you find this thing. The one is
Yeah, I don't know how I feel like there's a lot. Because for every single listing, it was just this a lot thing, which kind of fits with the big picture because it's not just PVP mass anymore, like 100 lines of other entries are not non-zero. The other entries are not non-zero. See, that's why it's different from just. As in like, you submit it, you know. They also have sizes.
All zero. The P and P reverse comes when you do a change of places. I think it's assuming that this matrix will only work if you put here, right, it's on the basis of this. and P inverse come about? This P inverse is probably to change this basis into its original basis. I feel like more P and P inverse is the change of basis. It's a transformation that since this change of basis from this basis to 0, 1, 2, 3 basis. Yeah. Because this, my answer from here will still be in my basis of being vectors, but I don't want that. So I do a P inverse and P to make it, you know. Yeah, that's,
Or just hypothesis.
Feel free to ask any questions. Feel free to discuss with your peers as well. Oh, you have a question? Right, try to somehow switch over.
Can you make it come up?
Yeah, maybe we do it.
Oh, I think I from here.
Yeah, just ask a question. Yeah.
I want to prove something is unitary, right? You
Yeah.
have to put A, then A dagger, right? Must I prove that A dagger A is also the identity matrix to show that it's unitary? I must show both ways.
So if it's square, if the matrix is square, then you just show one way, you know? But in general, you have to show both ways.
So at the end, I must show A dagger and A dagger A. Right?
Yeah, you should ideally do that. Yes.
Thank you.
Yes.
Can I ask why for the normal matrix they use the doubles in the arrow, but for the dyadic, that is equal. So are they not equivalent?
You mean A, B, and C?
Yeah.
So when we use the arrow, we mean represented by a bit. And when we use equal, it means that that's the action of the linear operator. Like that's how the linear operator is defined. Because remember that an operator has infinitely many different matrix representations, right? Right. Like depending on the basis, you can always express B with this like the B operator in a different matrix.
How do you represent a different matrix with a different basis? Or?
Yeah. So you have a different basis, then you can always express the same operator. It's exactly the same operator, but you write it as a different matrix. Right. I think that that's a key point I want to stress on, that a linear operator has a matrix representation, but it depends on what basis you're working with.
But then if you assume it says it's an orthonormal basis, then it's exactly equal.
No, it's not exactly equal. So the second part of the problem statement says that treat blah as an orthonormal basis, right? And the matrices as a representation in that basis. So I happen to write it in that basis.
Okay, thanks, bro.
But it's not true that when you change your basis, then you get the same matrix. You get a different matrix. The operator can be exactly the same.
Okay, thanks.
There's one.
In MM1, when you show a matrix as unitary, has there ever been a case where A times A dagger is equal to I, but then A dagger times A isn't equal to I?
Yeah, so I don't know the I think the linear algebra module, but then that one don't cover like the
Interesting dagger. But just now Prof saying you show both.
yes. In the linear algebra module, do you want to talk about numbers?
Yeah, I took linear algebra.
Which eigenvector, so you have the eigenvalues. But in the case of any other orthogonal basis, it will just be the HII, like the.
So what are you trying to show?
Trying to show that the diagonal matrix entry is of the matrix is real. So instead of writing eigenvalues, it will be just be HII.
No, but it's you want to show why this thing is good. I don't understand it. Somebody is reaching what?
So let's say you are not talking about diagonal, they will just take I choose and you get
Yeah.
so for the like if for the next question you try with UI
When I show the matrix is unitary, right? Let's say I show A times A dagger is already equals to I. Then just now I think I heard Prof say I was going to show A dagger times A also equals to I. But is there a case where A dagger is I, but then A dagger and A isn't equal to I? Is it possible?
yeah. So you multiply by one time. It's okay to show A. I can't think of when I think of I can't.
Or you can't think of one yet? There is an example.
I don't really see.
It's only one. Yeah, so
What? Oh, it's fine.
That's your work, right?
Yeah, it's fine.
That's your
Yeah. I'm getting really. No, honestly, this one is like, I think I went Malaysia before. Oh, I have $5. At that time I went with my family, then I converted and didn't show it.
Once we have that, everything. The other is also right. Giving you a linear matrix. I can always transform to that.
Great.